Okay, so we continue our discussion on finding forces on a translating body in potential flow. And in the previous lecture, we found two pieces to the force. So, there was one piece which involves the velocity of the body, and there was one piece which involved the acceleration of the body. And what we showed that for any object of any shape, be 2D or 3D, if it was moving with a constant velocity, then the force along the direction of motion, which is known as the drag, is 0. So, this is known as D'Alembert's paradox. So, a translating body, if it was translating with a constant speed or uniform motion, or you have a uniform flow past a body, either way, the body will experience no drag force. So, this is something which is at the crux of what we do next, which is going to understand effects of fluid viscosity. But before we do that, we have two things to actually address. One is, obviously we saw that in 2 dimension, if there is circulation, then the presence of circulation gives us a transverse force, a force that is normal to the direction of motion. So, there is a lift force that is independent of the body shape, the body size, depends on the velocity of the body and the circulation that it generates. So, again I am just qualifying this. When I say body shape and size, we are making this kind of an assumption that the circulation is arbitrarily specified. So, we need to think a little bit more regarding what is the source of this circulation, what brings about this circulation. Before we get on to that, we just want to close this part where we had a component of force that depends on the acceleration. So, I will just write that piece. So, you have your Fi, the force that the body is experiencing involves u dot k integrated over the body surface, and then the vector potential phi k Ni ds. So, is this quantity 0? Even if you have a u of t that was varying in time. So, if u dot of t was not 0, what would happen to this quantity? So, would there be a force that a body would experience? So, let us try to take some examples of this vector potential. So, we have already seen this vector potential both in 3D and 2D. So, let us try to actually find this vector potential in 3D and 2D and evaluate this force. So, when we did this in 3D, the vector potential was minus a cube by 2 r square n of k, and in 2D it was minus a square by r n of k. So, let us go back, minus a cube by 2 r square n of k minus a square by r n of k. When I say 3D and 2D, this is not for any 3D object, this is for a sphere and a cylinder. So, maybe I will just make that qualifier, otherwise it is not going to be the same if you have some other 2D object, the form would be different. So, we have computed these things. So, let us use these to compute the force. So, let us do this integral SP for the sphere phi k n I ds, which is minus a cube by 2 r square n k n I ds. Now, this is on the surface of the sphere. So, on the surface of sphere, r is the radius of the sphere, which is a, minus a cube by 2 a square n k n I, and ds is a square d omega. ds is the surface area. So, a square is the radius of a sphere. So, I have a sphere of radius a. So, the surface area element is a square d omega. So, I will have a square cancelling out here, and I will land up with minus a cube by 2 ni nk d omega over the sphere surface. Now, what is this quantity? What is integral ni nk d omega? This is now going to be a recall from tensors. We have done this in tensors. This is an isotropic quantity of order 2, which means it is proportional to delta Ik, and the proportionality constant we have computed was 4 pi by 3. So, this is minus a cube by 2 into 4 pi by 3 delta Ik. So, for a spherical particle, I am just writing the force, because the other part of the force, if you remember, is 0, right. The remaining force is a big 0. There is no circulation for a sphere. So, there is no other part of the force other than this particular piece. So, we are trying to check if there is a force that would be there in the problem. So, rho u dot k minus half 4 pi a cube by 3 delta Ik. Now, 4 pi a cube by 3 is the volume of the sphere. So, I have minus half rho volume of the sphere, u dot k delta Ik would be u dot I, and rho volume of the sphere is mass of the sphere. So, what I have now, that an accelerating or decelerating sphere in potential flow does experience a force. This is a very interesting result. We are saying always that if you have a body translating, doesn't experience any drag, doesn't experience any force in potential flow, that is only when it is in uniform translation. If the body was in some degree of non-uniform translation, which means it is accelerating or decelerating, there is going to be a force that is going to act on the body. And if you see that the force depends on the mass of the body, but in this case this is half the mass of the body. Now, let us work this out before we make more general comments. So, let us go back to for a cylinder. So, we want to find for a cylinder what is this force. So, once again we have the same exercise to be done, and for a cylinder we now have this as minus a square by r nk. So, let us do that integral. Sp is minus a square by r nk ni ds. Now, on the surface of the cylinder, r is equal to a ni nk, and what is ds? ds will be a d theta. Now, this is a circular cylinder, it is a 2D problem. So, there is a circular cylinder of radius a, and then the surface area in this case is basically the perimeter, which would be a d theta. So, you have minus a square n I n k d theta over the surface of the cylinder per unit length, which is basically the perimeter. Now, what is this? So, once again we go back to what we did for a sphere. So, should it be 4 pi by 3 delta Ik? So, when we wrote this down, ni nk d omega, where d omega is the corresponding angle whether in 2D or 3D, we said this should be delta Ik without any doubt, because it is isotropic. There is only one isotropic tensor of order 2, which is delta Ik. Now, what should be that constant? So, to find the constant, we said let us put I equal to k, which means this becomes ni d omega, and this becomes delta II. In 3D, you have the constant as integral d omega by delta II, which is 4 pi and the denominator is 3. In 2D, this constant is going to be integral d omega delta II, and integral d omega in 2D would be integral d theta 0 to 2 pi, which is 2 pi. In 2 dimension, a closed curve is going to subtend an angle 2 pi, and what is delta II in 2D? 2, right? It's 1 plus 1, it's 2. So, this becomes pi. So, in 2D, Ni Nk d theta is going to become minus a square pi delta Ik, right? We are almost done. So, the force per unit length that is acting on a circular cylinder is rho u dot k minus a square times pi delta Ik, or it is minus rho pi a square u dot I. Now, what is pi a square? Pi a square is the cross sectional area of that cylinder. So, if this is force per unit length, then you can find for a cylinder this would be minus rho times pi a square L, which would be the volume, and that would give me the mass of a cylinder. So, what we observe here, that for a sphere it is half its mass, whereas for a cylinder it is equal to its mass. So, in general, for any object, the force that it is going to experience due to its acceleration will be related to something that is known as an added mass. So, the reason why we are saying added mass is because when we say that mass times acceleration is sum of all forces, this is basically appearing on the right hand side as one of the force. So, if you were to take it to the left hand side, then you will actually say that mass times acceleration, which is u dot I, plus this added mass, which I am writing for a sphere. If I write it, it is half m, is equal to now any other force that might be there. Let us say gravity or something of that sort.
In the previous one, how you just introduce the added mass? Can I just
So, the force that it is experiencing, so this is basically the computation of the force. The force that a body is experiencing, that force is related to the acceleration and in terms of a quantity that is proportional to the mass. Now, the general expression, because what we did here was we did this for a sphere, we did this for a cylinder, these are all isotropic quantities. If you do this for, let us say, something which is like a pencil. Now, if the pencil is moving along its length and if the pencil is moving perpendicular to its length, in both cases the scenarios are very different. So, in both cases, if the pencil or an elongated object were accelerating, the reaction that you get will not be the same along its length compared to what it is along perpendicular to its length. So, which is why I have written this in terms of a tensorial quantity. So, this is to say that there is an acceleration reaction, that is there from the fluid, which can be viewed as an addition to your mass, which can be viewed as a, so if you think in terms of a sphere, if you say there was a sphere which was basically moving under the action of some external force, you will say that mass times acceleration is equal to sum of those forces. Now, because of virtue of it actually accelerating, there is this additional reaction that it gets from the fluid, which if I were to take it to the left hand side, it is as if there is an addition to the mass that I have in the problem. So, for a sphere this is capital M, but if you have some other shape it will be different. So, added mass is nothing but an acceleration reaction from your fluid, that when you start to change your velocity, the change in velocity is basically responsible in change in the energy of the fluid, and the change in energy of the fluid is basically what would be responsible for an additional force. So, one way to write that is if you say that I have a rate of change of your energy that would be related to a work being done due to an increment in your velocity, right. I do a small change in my velocity and that is basically going to change my energy. So, F dot du is basically that rate of change of the kinetic energy of the fluid. And this is something which becomes interesting, because now if you think in terms of, if you were to think of this in terms of momentum, say if P was my momentum, so momentum is defined as rho ui dv. This is a frustrating quantity in potential flow. The reason why I say it's frustrating quantity, because we know if you do a 3D problem, ui goes as 1 over r cube. dv, the volume element, will go as r square dr times some angle. So, when you look at this integral, you are going to get an answer which will be 1 by r dr d omega. And what is the answer that you get for the momentum will actually depend on the shape that you consider for your integration domain, which is a little bit of a frustrating kind of a calculation. So, as an exercise what I will leave you with, you can try this out. You know the expression for velocity, you know what is the potential, right, and the velocity for a translating sphere. So, for a translating sphere, phi k is equal to minus a cube by 2 r square n k, which means your velocity potential is minus a cube capital U bar cosine theta by 2 r square. You can calculate what the velocity components are, and let us say you compute what is your ux component of velocity, the x component of velocity. Try computing rho ux dv and consider two scenarios. Consider a case where there is a sphere enclosed inside a large sphere. So, I have a integration domain which is a spherical integration domain, and consider a second example where the sphere is enclosed in a large cylinder. So, here there is a radius capital R, there is a length L, here there is a radius capital R. What you will find when you do this calculation, that the momentum found using a spherical exterior surface will be 0, whereas the momentum found using a cylindrical exterior surface is non-zero. So, the point being is mathematically these are not convergent integrals, these are conditionally convergent depending on your integration volume, and that is frustrating because something as physical as momentum, we are having difficulty in trying to define what is the momentum. Then how do we go about defining a force which is the rate of change of momentum? So, the approach to take is to actually think in terms of what is the kinetic energy of the fluid, what would be the energy of the fluid. So, you already know what is the velocity. So, you can actually go ahead and compute this quantity and then try to find out that what is the change in kinetic energy due to change in velocity. And then you realize that change in kinetic energy is responsible for change in momentum. So, you will actually say that if I have a small change of momentum that is occurring in the problem, that can be related to a change that is happening in terms of my momentum. So, instead of actually defining the rate of change of moment directly by computing the momentum and trying to find the force, you rather can take an approach of finding the energy and find that if the velocity was to change, there was a sudden change in velocity, there would be a corresponding change in the energy, and the rate of change of that energy is related to a work that is being done due to that increment in velocity that is being done, and that basically gives me my force in the problem. So, we derived it using the Bernoulli equation and directly finding the pressure, but you can also take this particular approach. So, this is something which is of great importance, because you realize that if there was a body that was trying to move through a fluid and it does not move with a uniform velocity, the velocity was changing with time, there is going to be a back reaction that you would get from the fluid, and it is not proportional to, or it is not equal to, the displaced mass of the fluid. The added mass is not equal to the displaced mass of the fluid. It is to be computed in terms of what kind of shape do you have. Because if you think about it, that you consider a shape which is anisotropic in shape, you can have very clearly different kinds of directionality based on whether you move along the axis or you move perpendicular to the axis, and eventually this is the expression. So, finally, what you can write down, so to summarize, we have an expression of added mass which was UK rho phi k ni ds over the body surface. So, if I want to write it in terms of an added mass, mik UK, then mik will be minus rho sp phi k ni ds. So, it is a tensor that you need to compute given the corresponding shape that you have of the object. So, for every problem you can actually find out what is the vector potential, and then when you integrate of the body surface you would actually find this. So, we computed this for a sphere, you can compute this for a cylinder, and you can basically find this for other shapes. And this is of great importance when you are thinking of a lot of loading. If you think in terms of where do you have this thing being quite important, this is something that is of great importance when you are trying to design structures in the ocean. So, especially for designing any body that is basically there in the ocean, and if you ignore the effect of let us say viscous effects are not taken as a first order effect, you have constantly an oscillating flow, an unsteady flow that is impacting structures. So, you have let us say a cylindrical object that is immersed in the ocean, and to a great degree of approximation, the flow in the ocean can be approximated as a potential flow. So, you have an unsteady flow that is governing the wave dynamics in the ocean. Now, you want to find what is the wave loading on this structure, and to find the wave loading on this structure, you will basically know that there is going to be a loading that will come from this unsteady flow field, which would be related to the added mass. So, given any structure of any shape, you would be able to find what is the added mass tensor, and once you know the added mass tensor, you will be able to compute what should be the force that it should experience. So, that is where it becomes quite crucial to know the effect of added mass, that you have an additional reaction from the fluid by virtue of the fact that you are accelerating. Okay. So, this was the discussion regarding the unsteady part, where we saw that if you were to move with some non-uniform velocity, you would experience a force. The question goes back now to concluding our discussion on potential flow. So, to conclude our discussion on potential flow, we have the first question is regarding circulation. What is the origin of circulation? What brings about the fact that there is a circulation in the problem? So, for instance, we solve the problem of flow past a circular cylinder with circulation, and if you remember, we saw that for any non-zero circulation, we can have flow patterns which could look like this. We can also have, for higher circulation, we can also have something more complicated, but roughly speaking, you have a flow pattern that resembles this, and there was a lift force on this object. Now, one way to imagine this problem is if you can say that this circulation is related to the spin of this object. This circular cylinder is spinning and translating. So, this was obviously for a uniform flow, but you can be in a reference frame in the lab, in which case now you are looking at an object that is translating and spinning. And the answer that you get is drag is 0 and then there is a lift force. So, you try to move with a spin and then you experience a transverse force, which is all fine, and it gives you something which we classically know as the Magnus effect, that there is a lateral force that a spinning body experiences due to translation. But there is an important catch here. The important catch is, if the body were to spin and the body is a sphere or a circular cylinder, it can spin with whatever angular velocity it desires, but the fluid is not obligated to maintain that angular velocity. So, think of the problem that I have a circular cylinder, the fluid at t equals 0 is at rest, and I turn on the motor or I turn on the mechanism by which this cylinder starts to spin with some angular velocity omega. There is no way there is information that will pass on to the fluid that the cylinder has started to move, because the only information that the fluid cares about, what is the normal velocity, and the normal velocity was 0 earlier and it continues to be 0 later. So, for a perfectly inviscid fluid, if you think of an object which is a circular cylinder or a sphere, if you set it into motion, that motion is not going to get transmitted to the fluid. So, if you are trying to argue for circulation due to spin of the object and thus a lateral force, for the fluid to actually experience that motion, you need to bring in something else that is not there in the inviscid problem. How did the rotation of this circular cylinder get transmitted to the fluid which is surrounding it? How did the adjacent layers of fluid realize that the sphere or the cylinder has started to spin? Because you can always argue that u theta equals to gamma by 2 pi r, where gamma is equal to omega a square. So, omega is omega 2 pi a square, right. If you choose gamma is equal to omega 2 pi a square, then that will satisfy the boundary condition that the tangential velocity of the fluid is the tangential velocity of the cylinder at r equals a, and it is also a solution of potential flow. And now you can superpose this with the uniform flow and the doublet and you will get a picture which looks like this. So, there is nothing wrong in basically taking a velocity field which is u theta equals to gamma a square by r, adding this to a uniform flow and a potential doublet and finding a lift. But then you have to step back and then think, how did the fluid manage to actually start realizing that the cylinder is spinning? And this is the part where the role of viscosity starts to come in, that how was the fluid set into motion. If you translate a particle, if you translate a cylinder or if you translate a sphere, you have a cylinder which was at rest at t equals 0, the fluid was at rest at t equals 0. You make it move with some velocity. The moment it moves, immediately the fluid which is here, those fluid particles are going to get pushed away. It's like you are trying to move through a crowd. As you try to move through a crowd, you are basically going to throw people ahead of you out of your way. So all the fluid particles which are ahead of it will basically get thrown out, and people on the rear side are going to get drawn in. That is your potential doublet. So any translational motion is going to disturb the fluid. But if there is a rotational motion of an object like a cylinder or a sphere, there is no way I can disturb it. So even though this exercise of considering a velocity field which is consistent with the equations of motion and gives me a lift, there is something more to understand in terms of what gave you this circulation. So this is one part regarding the aspect of rotating object. But what if the body is not rotating? What if you have something like this? Does it need to have a spin in order to experience a circulation and thus a lift? What would be the source of circulation? So this, what we will be considering is a cylinder of elliptical cross section. We are not going to go through the exercise of how to solve it. This can be also solved in potential flow using elliptic coordinate system. I am going to spare that algebra and I will give you some references where you can look it up, but we will focus on the solution. We will not focus on the method of solving the problem. So I have a circular cylinder which has major axis of 2a and minor axis of 2b. There is a stream that comes in from infinity at some angle. Let me just draw this 1 minute. So 2a and 2b are the major and minor axis of this elliptical cylinder, and you have a stream that is coming in at an angle of attack angle of alpha, and we have this as our x coordinate system, this as our y coordinate system. So our classical Cartesian coordinates, if you know that in polar coordinate system, it is r cos theta and r sin theta, right, if you use your circular polar. But if you use an elliptical coordinate system, this will get modified. So this will be sigma 1 plus lambda square sigma by sigma square cos nu, and y will be sigma 1 minus lambda square by sigma square sin nu. So this is elliptical polar coordinates, where lambda is half square root a square minus b square. So lambda goes to 0 when a is equal to b. So for a circular cylinder, you recover what you originally had in the problem. So you have this coordinate system in terms of sigma and nu as your two coordinates which map to x and y. So I will directly write down the solution. As I said, like the exercise of finding this, you can look up the textbook of Batchelor or Milne Thompson, but again it is more of a method of how to solve potential flow in elliptical coordinate system, but that is not something which we will focus too much on. Rather, I am going to write the velocity, and not going to write the velocity also everywhere arbitrarily. I will write it only on the surface. So I will just put the velocity on the surface of this elliptical cylinder. So just bear with the equations for a little bit, and then we will focus on understanding what is happening. So a plus b sine nu plus alpha plus gamma by 2 pi by a square sine square nu b cos square nu, and then there is a b component b cos nu u square plus b square half a plus b sine nu plus alpha gamma by 2 pi a square sine square nu b square cos square nu. And you have the flow which is coming in at an angle has a component u comma v. Okay. So, these are the surface velocity components on the surface of this ellipse. Now, what happens when gamma is equal to 0? Gamma is the circulation. So, if there is a circulation in the problem, this is the expression, but if circulation was not there, where would the stagnation points occur in the problem? So, if gamma was equal to 0, you can check that ux is going to be minus a sine nu u square plus v square half a plus b sine nu plus alpha by something which is in the denominator that will never go to 0. Uy on the surface is plus b cosine of nu u square plus v square half a plus b sine nu plus alpha by the same denominator. So, I am measuring nu as the same way I am measuring theta. So, where does it go to 0? One solution is, if you put nu equals to pi by 2, then uy goes to 0, but then here I would have to have sin pi by 2 1, and here I would need to basically have pi by 2 plus alpha, which would actually have to, so I will have a value of alpha that would be only applicable for a very specific value of alpha where it will be 0, right. But what about any arbitrary value of alpha? I am not interested in one specific value of alpha. So, if I am interested in one specific value of alpha where this should be 0, is where I will have one location which would be when nu is equal to minus alpha, because if nu is equal to minus alpha, you can see automatically that ux is 0, uy is 0, right. If nu is equal to minus alpha, it automatically goes to 0. Similarly, you will have nu is equal to pi minus alpha, that will also give me a stagnation point. So, I am going to basically get stagnation points at minus alpha and pi minus alpha and see that those are the locations where the velocity goes to 0. So, first let me mark the stagnation point. So, there is a stagnation point which is basically here, and there is a stagnation point which is on the, so there is a forward and rear stagnation point that I have. So, this is my forward stagnation point, and then there is a rear stagnation point. So, one is at minus alpha and the other is at pi minus alpha. So, now let me sketch the streamline. And similarly near the rear stagnation point, so this is what the flow field will look like for flow past an elliptic cylinder at a given angle of attack alpha. there are these two stagnation points. Now, if you were to increase gamma, if you were to basically keep changing your circulation, what should happen to the stagnation points? Now, you can basically try solving these equations, you can try to actually look at what is happening to the equation, but we will take a slightly easier route. The easier route we will do is, we will take a consideration where B is equal to 0 and A is non-zero, which means that the major axis is squeezed and the major axis remains finite, the minor axis goes to 0. So, this is basically going to be flow past a flat plate. So, to see what circulation does. So, we will have the stagnation points. This is the picture that we will have, and if you go back to your expression, you can see that on the surface of the plate, as it should be, uy is 0, B is equal to 0. So, uy is 0, there is only a ux velocity. So, you will have a ux velocity which will be minus u square plus v square to the power half a sine nu plus alpha minus gamma by 2 pi a sine nu, and obviously uy is equal to 0 at the plate. So, if you have 0 circulation, then your stagnation points in this particular problem would be the way that I have marked it out in these cases. Now, where is the problem? Where do you have a problem here? The problem that you have here is that if you look at nu equals 0 and pi, so this is the forward stagnation point, this is the rear stagnation point. You see at these two corners, what is the surface velocity of the fluid? Ux goes as 1 by sine nu. If the circulation was absent, so when gamma is equal to 0, if there was no circulation, then ux at nu equals 0 is infinite. Ux at nu equals pi is also infinite, which means at the leading edge and at the trailing edge, the surface velocity is infinitely large. So, what is happening here is that when you do not have any circulation for an object which is like this flat plate, the two tips that are there, the two ends that are there, the corners, have infinite fluid velocity. So, this is where we need to take a step back and try to think in terms of what is going on. What is going on is here, the fluid that is coming here, it is bending around that sharp corner. It bends around this sharp corner, here it bends and goes back, and then here again it is bending in this location. So, if you choose a value of circulation, so now if you choose your value of circulation as 2 pi a u square plus v square to the power half sine alpha. So, you go back here. So, if you, so your ux was minus u square plus v square half a sine nu plus alpha minus gamma by 2 pi a sine nu. Now, if I choose this exact value of circulation, then it becomes minus u square plus b square half a sine nu plus alpha minus gamma by 2 pi, which is a sine alpha u square plus v square half a sine nu, which is minus u square plus v square half a sine nu plus alpha minus sine alpha sine nu a. So, what happens when nu is equal to 0 and when nu is equal to pi? So, the question is, where is your stagnation point right now? Earlier, when gamma was equal to 0, your stagnation points were at minus alpha and pi minus alpha. Now, if I choose this specific value of gamma, that gamma is equal to gamma star, where is my stagnation point? So, there is one which is going to be at nu equals to 0, right? And then so if I put this as, one sec, there was a minus sign here, right? I missed the minus sign. So, nu equals to 0 will not be a stagnation point. Nu equals to pi will be a stagnation point. So, now what happens is the forward stagnation point will shift, but it will stay on the surface of the plate. But the rear stagnation point, which was earlier at nu equals to pi minus alpha, has now shifted and come to the trailing edge. So, the rear stagnation point is coinciding with the trailing edge. So, the trailing edge, which was earlier a location of infinite velocity, you were able to mitigate that by having the stagnation point shifting to that location. So, there is something special about this value of circulation. So, what I have shown so far is I have just said, if you were to take this magic value of circulation, then the trailing edge, which was earlier a location of infinite fluid velocity, will coincide with the stagnation point, the rear stagnation point, and you remove this singularity in the velocity field. So, there are now again it comes back to two questions. Why this magic value? How does it drop out of the sky? And the second point is, why does it actually happen to be there? Like, why does the trailing edge automatically going to coincide with this rear stagnation point? So, that means you go back to this particular picture which was there for zero circulation. So, the fluid in both these regions is basically undergoing, it is trying to turn around here. So, the fluid bends around that particular location and it is going around this and moving away. So, when it does this at this particular location, and this is something which we are going to borrow, and we are going to go a little further ahead and borrow a concept, and we will see this formally later, that this aspect of the fluid trying to go around this trailing edge will lead to a separation. It is very difficult for the fluid particle to actually go around this sharp knife edge. So, as it tries to go around this knife edge, gradually what will happen is it is going to have these streamlines cannot bend any further, and at some point it is going to eventually separate out. What does it mean? You have this scenario where it is doing this. So, let me draw the cartoon. So, it is trying to actually bend. So, now if I zoom in here, the fluid streamlines are doing this. So, at some point near the trailing edge, it gets very difficult for it to do this strong bending of the streamlines there. So, then subsequently what you will observe is that this bending will lead to a separation. So, I have drawn a small vortex there. The streamlines cannot arbitrarily bend. You have very high velocity at that location. So, it is trying to bend around. As it tries to bend around, eventually it is going to separate at that location. And this, due to viscous effects, that vortex is basically going to grow. And finally, this vortex is going to get detached. So, by this process of detachment, what is happening is, what was earlier your stagnation point that was located away from the trailing edge, that is going to gradually come closer to your trailing edge. So, the rear stagnation point that is there. So, in this region you are going to create a separation, there will be a separation in this region. So, I am explaining what is going to happen in the real problem. In the real problem, you pull a plate. As you pull a plate, there is a forward stagnation point and there is a rear stagnation point. So, at the rear stagnation point, because there is this huge bending around that is occurring of the streamlines, eventually there will be a separation which will happen and a vortex is going to get shed and it will move away. This shedding of the vortex will lead to the rear stagnation point migrating towards the trailing edge. It will continue until eventually the stagnation point is going to coincide with the trailing edge. So, the value of circulation is not arbitrary. The value of circulation is just the right amount which makes sure that your trailing edge has a finite value of velocity, or the stagnation point is coinciding, the rear stagnation point is coinciding with your trailing edge. Now, you can always say, I have been a bit covering up things here by not addressing what is happening in the leading edge, because leading edge also the velocity is infinite, right. When we said the velocity is divergent, the velocities were divergent both in for leading and trailing edge. Nu equals to 0 is also infinite velocity, but that you can mitigate. That you can mitigate by actually rounding up this region. You can think of this now like an airfoil where the leading edge is rounded up. So, when you round up the leading edge, the velocity there is going to become finite. And the separation, which is basically the infinite velocity and separation, there are two things happening here. The infinite velocity from the potential flow argument, and the fact that when the fluid is trying to curl around, that curling around of the fluid is going to lead to a separation, which is eventually responsible for your stagnation point to move towards the trailing edge. So, the value of circulation is not something that you go and add into the problem. You are not adding anything in the problem. You are saying that in the problem, the flow is eventually going to adjust to a value of circulation. So, constantly this process will happen in the initial time instant, and then finally in steady state, it will adjust to a value of circulation which is consistent with the stagnation point coinciding with your trailing edge. So, this is basically at the heart of how we have circulation coming in the picture. So, the fact that for a two-dimensional body, the value of the circulation is decided based on having the rear stagnation point coinciding with the trailing edge. This is known as the Kutta condition. So, we all spoke about this when we did the circular cylinder problem, that what is gamma? What is the value of gamma that you have? Now I am basically putting a unique value to the value of gamma. So when you are doing a problem where you have a forward, a trailing edge and a leading edge when any two-dimensional body, so the Kutta condition or the Zukowski hypothesis, both names are there, decides that the value of circulation is decided so as to have your stagnation point coinciding with your trailing edge. If it is some other value, if gamma is less than gamma star, then what will happen? If gamma was value less than the value of gamma star for that particular problem that we chose, there will be immediately a vortex that is going to be shed at that corner. So if you go back to this corner, if the value of gamma is smaller than gamma star, then there will be a vortex which will get shed here. It will move out. As it moves out, the stagnation point will keep adjusting till you have the stagnation point exactly coinciding with your trailing edge. So that then gives you the specific unique value of gamma that is there in the problem. So when you are designing these problems and you are looking at the flow field, what value of gamma you choose is decided based on the fact that eventually the flow will have the stagnation point sitting at the trailing edge, and that is how you make it unique, the value of gamma. And that then decides what is the value of your lift. So both the value of gamma and the origin of gamma, the value of the circulation and the origin of circulation is actually from viscosity. If there was no viscosity in the problem, there is no separation in the problem. If there is no separation in the problem, all of these would be valid solutions. The infiniteness of the fluid velocity is basically satisfying whatever it has to satisfy in terms of its boundary condition and governing equation, but it is unphysical. And that unphysical nature of the velocity, which then manifests in terms of separation, is all possible due to viscosity. So the calculation of lift is not a viscous calculation. It's a calculation that is completely inviscid in nature. But the origin of the lift or the origin of the circulation is at the heart is from viscous effects. See, in this problem, viscous effects, once the vortex gets shed, once you have the streamlines starting from the trailing edge, the stagnation point being there, you again stop talking about viscous effects. Again you are saying there are no viscous effects in this particular problem, the flow is inviscid everywhere. But you don't arrive at this, because this is a valid solution, and so would be a solution where the streamlines basically have a stagnation point here. There would be a valid solution if you were to have a stagnation point somewhere here. So let us say this is gamma equal to 0, this is gamma equal to gamma star by 2, and this is gamma equal to gamma star for this problem. All of these are solutions, because I have no physical basis in this problem. When I said there is a flow at an inclination angle of attack alpha on incident on this airfoil, I have nothing else as an information. So what does it choose as a value of gamma? Does it do the problem with gamma equal to 0, in which case the rear stagnation point is somewhere on the body and the trailing edge has infinite fluid velocity? Does it do some other value of gamma, or does it make a, so you decide the solution, you pick the solution based on viscous arguments. The solution is inviscid, but the choice of the solution is motivated based on viscous arguments. So finally, if you do your calculation of how the circulation comes in, so the final picture is you have an airfoil that is translating with some velocity. There is a vortex that is going to get shed, and eventually you will find this vortex detaching from the body and somewhere here. Now you consider your domain. This is what has happened. The vorticity got shed from the body. Now the total circulation of the problem is 0. There was zero circulation to begin with, there is zero circulation at later time. So, circulation theorem tells us that the total circulation around this particular circuit, if it was 0 at t equals 0, it remains 0 forever. Now, if I draw a box which encloses this starting vortex, this has some circulation. Let us say the starting vortex is basically spinning in the clockwise direction. So, this has a circulation which is minus gamma, which means this body has a circulation which is plus gamma. The body is not spinning. The body attains that circulation because it has released out a starting vortex. So, when the problem starts, there is viscous effects at play. Viscous effects are responsible that initially whatever is the flow is, automatically the stagnation point is not necessarily going to be, when the body is in motion, is not going to be exactly at the trailing edge. There will be a separation process that will go on, there is a vortex that will be generated at the trailing edge, it will get ejected out and it will get swept downstream. This process will keep continuing till you have a flow pattern where the trailing edge is your rear stagnation point. After that, any further shedding is not going to happen. And then what is the circulation that is generated by these vortices that have been swept out is exactly what the body is going to acquire. That is another way of looking at it, the exact magnitude. We did these calculation for a plate, but for any other body, this is how it will going to happen. So, this is at the heart of how we understand how potential flow theory is used to get a feel or get a calculation for lift. That the calculation of lift mathematically is an inviscid calculation, but it does not make any sense unless you poke it deeper and try to understand what gives you that circulation, what is the source for that circulation. So, to understand the source of circulation, you have to go into how viscosity is playing a role. So, viscosity does that initial adjustment and then its job is done. Once its job is done, then you can almost assume that there was nothing to think of viscosity and go ahead and do your calculation. Okay. So, with that I will end. That is mostly what I had to discuss regarding potential flow. And I guess this is a good place to end potential flow, because you have now probably starting to think about viscous effects. So, the next thing which we will do will be on viscous effects.